Okay, let's suppose we're given a problem like this one where I've got a function x of t that's periodic, and I want to be able to compute the Fourier series coefficients for this waveform, and I want to do it numerically. And in particular, I'm just going to assume for now that all I want to do is to calculate the DC value of this particular waveform, which is given by this expression right here. So that's all I'm going to focus on right now. Now, I want to do this numerically, and I want to assume that I've been given the signal x of t. In other words, I don't have to actually create a function for it and perform the integration. In other words, I don't need to say, like I do here in this case, that x of t equals 2t from 0 to 1, and then 0 from 1 to 2, right? That is true, but I'm going to assume that I'm given x of t. Now, in looking at this particular waveform, you should be able to see that just in this case, I can figure out the exact value of this integral, the average value, pretty easily. T is equal to 2, so I would say 1/2. And then that integral would be just the area under the curve, which would be 1/2 the base times the height, which is that. And I would be left with 1/2, okay? But we're going to assume instead that we're going to try to do this numerically, and I just wanted to do it this way so that we can try to understand how to perform numeric integrations. So x of t in this particular case, which I'm given, was sampled at 5 kilohertz, okay, which means that the sampling frequency, or the time between samples, was 1 over f sub s, or 1 over 5,000, okay, and I know that it starts at time t equal to 0. Okay, so we're going to take a look at that signal and that problem here in a second. Before I do that, though, I need to understand a little bit more about numeric integration. All right, so the idea of numeric integration basically comes from the definition of the integral, which we have right here. Okay, basically what I say is if I want to get the area under a curve, the way I can do that is by drawing rectangles underneath the curve and essentially trying to figure out the area of each of these rectangles. All right, so that area, basically what you're doing is you're summing up the area of each rectangle. So in each of these cases, this width here is t sub s, okay? And essentially what I'm doing is I'm saying, well, the height of this rectangle is given by the value of the function x of t, and the width is given by t sub s. Well, if I think about the meaning of the integral is, well, just sum up the areas of each of these rectangles. Okay, that's the meaning of an integral, and that's what this says right here. All right, which basically what we do is we allow t sub s to get all the way equal to 0, which if I allow t sub s to go all the way equal to 0, it becomes the integral. Now, just as we did before, I want to replace this limit with an approximation sign, which is what we do whenever we're inside of a computer, because we can never let anything go to 0. In other words, I can't let the width of this rectangle get infinitesimally small, and then I would have infinitely many rectangles to deal with. Now, the tricky thing about this, you learned this back in calculus, is this idea of trying to sum up the rectangles becomes kind of trivial if I actually do the integral, but if I'm actually trying to compute this approximation, this gets a little bit tricky. There's effectively 3 ways of calculating these areas. I use either the left sum, the midpoint sum, or the right sum. All right, so essentially when I say the left sum, what that means is the left side of the rectangle touches the curve, and then I draw the rectangle with t sub s from there. In the right sum, I basically have the rectangle touching the curve x of t on the right side of the rectangle. Now you can see that the left sum basically is going to underestimate the true area, so it's going to underestimate the true integral, and the right sum is going to overestimate the true integral because it's taking into account an area that's outside the curve, whereas the left sum is missing it. All right, so if you think about it though, if I take the actual true integral and I let t sub s equal to 0, this area that's missed in the left sum is going to go to 0, and this extra area in the right sum is going to go to 0. Now sometimes people use the midpoint sum. All right, the midpoint sum would appear to be a little bit more accurate because it does a little bit of overestimating of the area, so it calculates some area outside the curve, but it also misses some area inside the curve. All right, if my t sub s is sufficiently small, it really doesn't matter which one I pick. All right, and we'll see that as we go. All right, I think the easiest thing to do is to choose one of them and to choose the easiest one. The midpoint sum may be the most accurate, but it's probably also the most annoying to choose, as we'll see here in a second. All right, so let's compare the left sum and the right sum just to try to see if we can understand it. So let's say, I'm going to call this guy, I'm going to say he's sampled t sub s, 2t sub s, 3t sub s, 4t sub s, and 5t sub s. And similarly for this guy, so t sub s, 2t sub s, 3t sub s, 4t sub s, and 5t sub s. Okay? So let's compute the left sum. Here's the formula for the left sum down here, and let's kind of evaluate that. So in this case, I say n equal to 0. So let's say I wanted to do this for, just to keep things simple, let's say I just want to do this up to 2t sub s. All right, so I'm going to evaluate this sum. Well, to do this, I start at n equal to 0. So I say I have x of 0. So x of 0 is this point right here. Right? This would be x of 0. This point right here would be x of t sub s. And this point right here would be x of 2t sub s. Okay? So in my left sum, if I wanted to get the area between, so just to be clear, what I'm trying to do is I'm trying to get the area under x of t from 0 to 2t sub s. Okay? So I'm trying to compute that integral. So if I use the left sum, I say I start at n equal to 0. So at n equal to 0, I have x of 0 times t sub s. All right? That's the first term. That is this area right here. Okay? Then I want to add in the next area. The next area would be x of t sub s times t sub s. Okay? In other words, the width of this guy is t sub s. That right there, I'm saying, is the area from 0 to 2t sub s, because I've included this rectangle and this rectangle. Okay, that covers everything up to 2t sub s. If I did the right sum over here, well, in that particular case, notice that I've shifted everything here. I go from n equal 1 to whatever point I need to stop at. So I guess I didn't define this, but I said for n end, it looks like n end should be equal to 2, right? Because I'm summing over two rectangles. Okay, so in this case, it's still equal to 2. Okay, now I say I start with n equal to 1. So just to remind ourselves, this here is x of t sub s. This value here is x of 2t sub s. So what I do in this case is I say, well, x of t sub s times t sub s, this is what I get for n equal to 1. And then I have x of 2t sub s times t sub s. This is what I get for n equal to 2. All right? So the area of the first rectangle, this guy. Area of the second rectangle is this guy. Now notice, in both cases, both on the left, both with the left sum here, so both with the left and with the right, in both cases, I've approximately computed the area under the curve between 0 and 2t sub s. All right? Basically, and I had to use 2 points from the curve to be able to do it. In the first case, what I did was I start with the first value, and I don't include the last value. Whereas in this case over here, the right sum, I don't include the first value, but I do include the last value. All right, so we're gonna try to bear that in mind, and I'm gonna focus on using the left sum because I just think it's easier. All right, so let's imagine we're trying to compute that value over that function. This looks a lot like that x of t that we looked at on the first slide. In other words, looks a lot like this x of t, right? It's ramping upwards. All right, so here I have all my rectangles, and I've said, okay, well this point is 0. This is time t sub s. This is time 2t sub s, 3t sub s, 4t sub s, 5, 6, etc. And I've drawn in here each of my rectangles. So I can see that the width of each rectangle is t sub s. All right, and I've marked out the values on the curves. This is x of t sub s, x of 2t sub s, so on and so forth. So let's try to evaluate this integral here using the left sum idea. All right, and this will help us to think about how we would code this. All right, so the first thing I would do is I would say, well, so in coding this, I would use a for loop. In that for loop, each time through that for loop, I would increase n end and t end. So there was the first time through this, let's say, so first pass, I would have t end equal to t sub s. So I would have n end equal to 0. Okay? And what I would do is I would say the integral from 0 to t sub s of x of t dt is approximately the sum from n equal to 0. Sorry, I should say n end is equal to 1. So I go from 0 to 0 of x of t sub s times n times t sub s. That's just going to be x of 0 times t sub s. Now in this particular case, that's equal to 0, right? Because I see that x of 0 there is equal to 0, right? There's no height to that triangle. Okay. Now again, that looks like an error, and it is, but if t sub s is really small, then that error turns out to be pretty negligible. All right, so now we do our second pass through the loop. Now we want to know the area up to t end equal to 2t sub s, which means that n end equals 2. Okay? And I'm going to say I'm going to integrate from 0 to 2t sub s, x of t dt. That's approximately the same as the sum from n equal to 0 to 1 x of n ts times ts, which is the area under the first rectangle, which we said was basically 0, plus now the area under the next rectangle. All right, so we've added in this rectangle right here. All right, so then my third pass, now I say, well, t end equals now 3ts, okay, and n end equals 3. So I take my integral 0 to 3t sub s. Now I'm going to add in the area of this third rectangle, x of t dt, and my sum goes from n equals 0 to 2 x of n ts times ts. So that's x of 0 times t sub s, the first rectangle, plus the second rectangle, plus the third rectangle. So that would be 2t sub s times t sub s. Now, I keep going with this, right? If I did the next integral on the fourth pass, so from 0 to 4ts, x of t dt, all right, it should be pretty obvious that this whole thing is going to end up being equal to x of 0, t sub s, plus the second triangle, plus the third triangle, plus the fourth triangle, and so something I notice as I go through this, right? As I went from the first pass to the second pass, I have my area from the first pass already there. When I go from the second pass to the third pass, I have that same area already there. When I go from the third pass to the fourth pass, that same area is already there. So in other words, every time I go through this for loop, all I do is add on the area of the newest rectangle. So that sort of says that the for loop that I want to do basically should keep track of a variable called sum, right? Or something like that. And then I want to add in the area of the new rectangle. Area of new rectangle. In other words, I could perform the sum each and every time through the for loop, or I could just keep a running sum and just hold on to the value that I've already gotten and then add on the new value as I go through that for loop. Okay? So let's look at how we would code that. Before we do, let's ask ourselves a little bit about how we would approach this. So I like to think about my code, and you should think about your code before you do it. And I box here some important things to remember. So I want to clear all my variables at the starting point. I want to make sure to use variables rather than hard code as much as possible. All right, so I got to think about this. Now remember, what we're computing is the area under the curve. All right, so the area over a period. And I'm given that x of t is this. And the x of t that I was given goes from, is this guy, and then repeats like that, okay? And I was told that the sampling frequency was 5,000 hertz, all right? Which, and then I'm told that everything started, and that x, the first entry of x, so x of t starts at t equal to 0. In other words, the first entry in x of t is at t equal to 0. Okay? And I was given one period, the first period of it. Okay? The first question I asked myself is, what do I expect my output to be? Well, I expect the output of my code to be a single constant, a single number. And it's going to be a real number. And I know that it's going to be a real number because I'm computing this integral, right? Which is simply a real number. If I'm computing the average, that's never going to be a complex number, right? The area under the curve can't have a complex relation. It can't have an imaginary part, essentially. I guess it's always complex, but it can't have an imaginary part. It has to be real, right? Because it's an average. All right, so how do I need to structure my code? Well, I know that what I need to do is I need to integrate over one period of the input, okay? So that means that I need to integrate from 0 to t, which in this case is 2. All right, so the question that I need then is, okay, well, how do I get the integration that I want? That's basically the next question I ask myself. So I got to figure out, where do I need to start and where do I need to end? Well, I need to start at t equal to 0, and I need to stop at t equal to 1. In other words, I don't need to go all the way through this thing, all right? I don't need to go all the way from 0 to 2, because I know that from 1 to 2, this thing is basically equal to 0, okay? So what do I need to create? All right, I need to create a couple of vectors. I need something for my output. This isn't really a vector. This is just a single variable, which is just one real number. Okay. I need to create a vector t that should have the same size as x. Okay, and I was told that f sub s is equal to 5,000. All right, so if that's the case, I'm going to need to do a check to see size of x. All right, and I'm going to need to create t, since I know that it starts at 0, it's going to go from 0 to 0, and it's going to increase in steps of t sub s, where t sub s is equal to 1 over f sub s. And I'm told that I'm given it over one period. So I don't know where to stop exactly, because I need to make sure that I stop at something given by the size of x. Okay. All right. So I know a couple of things now. All right. I'll need to figure out, where do I start? What index do I start at? Once I know a little bit more about the t vector. One thing I already know right now is if I'm going to start my integration at the very beginning of the period using the left sum, that means that I start at x. Now I got to be careful about this. We say we want to start at x of 0. Well, in Matlab, that means it's the first entry. So that means I want to start at what in this case I'm going to call the first entry, n equal to 1. All right, the first entry in the vector. That's a little bit confusing, right? We say x of 0 to mean at time t equal to 0, but that's the first entry in the vector. All right, so now I need to figure out, where do I stop? So if I'm using the left sum, right, I basically need to stop right before this guy gets equal to t equal to 1. In other words, I need to stop at basically t equal to 1 minus t sub s. And I need to figure out what index that equals. Okay. Well, at this point, let's go over to Matlab. All right, so here's the code that I wrote. Okay. So I knew the period was t equal to 2. All right. I called it delta t. All right, let me call it instead t sub s, my sampling interval. All right, this works out to be 1 over 5,000. All right, 2 over 10,000 is 5,000. And then I created a t vector that goes from 0 to t, 0 in steps of t sub s, all the way up to t. Now, how do I know that it has to go up to t? Well, the reason I did that was because I knew the size of x. So my x is stored inside of this mat variable. So let's go over to my command window, paste this in there. All right. So I look at this guy and say, what's the size of x? Well, x is a row vector with 10,001 columns. All right. So I know that he has 10,001 columns, and I know that his first entry is 0, which is the value of the function of t equal to 0. So that meant that this guy, my time vector, must include the very first entry in the period and the very first entry in the next period. Okay? If I really wasn't sure about that, one thing I could do is, since I know it has 10,001 entries, I could say t vector goes from 0 to 1 to 10,000. Right, that would be 10,001 entries, and I multiply by t sub s. Okay, that would create the exact same time vector. Okay, all right, then I plot this guy just to see what he looks like. I'll evaluate my selection. Okay, so I see he goes from 0 to 2 and then goes down. All right, so I want to figure out where my stopping point was here. All right, now I know that because I have 10,000 points in a period, all right, what I had said before is I want to go up to basically 1 time step before 1 second. All right, so I know that that's going to be somewhere around entry number 5,000 or halfway through this vector. So in this case, all right, what I'm going to do is I'm going to say, let's go to, what is t of 5,000? Well, that's 0.998. All right, so what's t of 5,001? Well, that's 1. All right, so it would appear that this guy here, 0.998, or t of 5,000, that is basically what I was looking for, which is basically 1 time step, 1 t sub s value before 1 second. So that means that I want to go to n equal to, so I'm going to go to n equal to, in this case, n equal to 5,000. Okay. All right, so I know where to start, n equal to 1, the first entry, and I want to stop at the 5,000th entry. Okay. All right, so, and I've created my t vector now. So I've done everything I need to do. Okay. So then what I do is I write my for loop. Now in this case, alpha 0 is what I'm calling my output. And my for loop goes from I equal to 1 to 5,000. Notice I called it I in this particular case. All right. So what I do is I say, all right, every time through this vector, I basically add on to the sum. All right, so the sum is alpha 0. So I take whatever it was before, and I add on to it the area of the newest rectangle. Now, since I renamed delta t to be t sub s, I'll write it like that. Okay, now notice what I do at the very end is I multiply by 1 over t because I'm computing an average. Okay. Then what I've done here is I calculated the percent error. So I know that the actual value of the area is 0.5. So I take whatever my alpha 0 is, I figure out the difference between that and 0.5 and calculate a percent error. So let's run this whole thing. All right, and let's go over to the command window to see what we got. All right, what I had at output was the percent error. So let's have it tell us alpha 0. Alpha 0 is 0.4999, so it looks pretty close to the 0.5, and I can see that the percent error is 0.02%. So it's incredibly close to the true value. Okay, so if t sub s were a little bit smaller, that error would go down even further, but my error is still pretty darn small at 0.02%. That's not 2%, because notice I multiplied my error by 100. It's 0.02%. Okay? All right, now what if I had a more complicated problem and I said, you know what? What I actually want to do is I want to calculate the complex Fourier series coefficients, and I want to do it for the first n harmonics. Okay? So let's think about how I would structure that code. Again, first question I ask always, what do I expect my output to be? All right, well, if I'm figuring out the n complex Fourier series coefficients, I know that that means I'm going to get, so if I was doing just the fundamental, let's say, so n equal 1, so just the fundamental would mean n equal 1 and minus 1. Just the second harmonic would be n equal 2 and minus 2. So in other words, I have to compute 2 values to get each harmonic. In the special case of DC, I have to do, so n equals 0, DC, 0 frequency. There's only one 0 frequency. It doesn't have a negative component. So that means that if I wanted to compute the first n harmonics, including DC, I would get a set of complex numbers, right? And I would have 2 times n plus 1 values. So think about that for a second. If I wanted to do the fundamental and 0, I would have 3 values, right? 1 for DC and then 2 for the harmonic. So it's always going to work out that I'm going to have 2 times n plus 1 values. All right, so that means that, you know, when I ask myself what vectors do I need to create, well, my alpha vector should have 2 times n plus 1 entries, right? And then I say, well, I should think about whether I want that to be a row or a column vector, right? I would create a vector for this guy, and it's up to me whether I want to make it a row or a column, right? So how do I need to structure the code? Well, again, I need to integrate over one period of the input, but I need to do it 2 times n plus 1 times. In other words, I got to compute this integral right here, right? I got to compute it once for n equal to 0, twice for the fundamental, meaning for n equal 1 and n equal to minus 1, and then I got to do it for n equal 2 and minus 2, and then for n equal 3 and minus 3, okay? So if I think about this, that means I probably want 2 loops, right? I have an outer loop that loops through each harmonic. In other words, I'm going to loop through it 2n plus 1 times. And then I'm going to have an inner loop that basically performs the same integration that I showed right here, all right? So again, I have to ask myself, is there anything different for each time I compute that integral? So each time I go through that, what I call inner loop. And then I have to think about how I set up the integrations. Okay? So I say an outer loop. So basically I would have, essentially for, n equal to minus n to 1 to n, something like that. And then I would have some inner for loop that does the integration. Okay. Now, I point out down here that I probably want n to be a vector of harmonic numbers, right? That's the way I probably would do it, and I would say n is equal to a vector that goes from minus n to 1 to n. And what I would do probably instead is, instead of looping on n here, right, what I would do is I would probably say for k equal to 1 to 1 to length of n, right, what I probably would do is, inside of my for loops, I would use n of k, all right? I think you'll find that that'll ultimately be an easier thing to do. But those are the sorts of questions you got to ask yourself as you set up your code. What do I expect my outputs to be? How should I create my variables to be able to hold the results that I want? If you think about those, it becomes relatively straightforward to do this. All right, the other key takeaway for you is really think about why it makes sense to set up the integral using a for loop like this. Because essentially every time I go through the for loop, I'm just adding in a new rectangle, basically the area of a new rectangle. And I notice that all of the other areas I can just hold in one variable. I can sum them all up and hold them in one variable, and then just add in the area of the new rectangle, and it becomes pretty straightforward.